It's my pleasure to welcome someone who is no stranger to NCAR and needs no introduction. Dr. David Parsons is a professor and director emeritus of the School of Meteorology at the University of Oklahoma. However, before his hallowed tenure at OU, Dr. Parsons was a senior scientist at EOL, and at one time also served as the deputy director of EOL. Dave was also a United Nations diplomat serving as chief of the World Weather Research Division at the World Meteorological Organization out in Geneva. His accolades are too many to list, but important to this group, Dr. Parsons is a fellow of the American Meteorological Society. Dave currently serves on the NSF's Advisory Committee for the Geosciences, the Fellows Selection Committee for AGU's Atmospheric Science Section, and other NSF-funded efforts. Dave's research and teaching interests include remote sensing, rainfall extremes in association with climate change, convection and mesoscale processes, atmospheric modeling, and AI applications. Whew. He will be merging many of these research topics in his seminar today, which is titled Nocturnal, Convective Systems and Their Broader Relevance to Weather and Climate. For those of you online, we are answering questions via the interactive Slido window, which is at the bottom of the presentation screen, so please don't hesitate to ask your questions anytime. During the presentation, we will table them for the Q&A at the end of Dr. Parsons' talk. Dr. David Parsons, we welcome you, and the stage is yours.
Well, thank you for that introduction. It's nice to be back here. And I'll start maybe with a little bit of an apology because, during the pandemic, you weren't giving live seminars that much. You weren't traveling. So there's a bunch of travel money left in the grant for students and myself to go places. But I think I probably combined far too many things into this talk. So we'll just skim on a lot of topics. At the University of Oklahoma, we start with a land acknowledgement that we're essentially living on land that was taken away from several tribes, and then there was 31 tribal nations that moved there. And then just to stay in the good graces, then I just put up the grants that supported this research, and includes Jason Furtado's grant. And I'll start with why convection. So there's people in the audience like Morris, you don't have to ask him why convection, but according to the great study by Carolyn Reynolds et al. 2019, the representation of deep convection was ranked as the largest source of systematic errors in the world's weather and climate modeling centers. So I know that Susan Gray, Professor Redding, said she always puts this up at the beginning just to make the aerosol people angry, but it was the source of what came out in the survey as the #1 problem they were doing. And then we know that rainfall extremes are increasing in our warming climate. There's some references there. And then people may not realize with the both climate change and the shift in demographics, people moving to coastlines, people moving to river valleys, that the risk is going up. There's about 20% of the world's population lives in substantial risk of a 100-year flood, and this is a WMO paper. And then just to go on a little bit more, started with why convection and why nocturnal convection. There's some great papers involving Peter Bechtel at the European Center, and then also Tang et al., which was, I believe, a climate modeling paper, that the accurate representation of elevated nocturnal convection and propagating nocturnal MCSs that occur over land masses remains the major challenge for weather and climate models. So just a little bit of a background, and then why nocturnal convection over the Great Plains. It's long known that, and the other references touch on this too, Peter Bechtel's, that nocturnal convection over the Great Plains tends to have low predictive skill, and MCSs over continental North America are predicted to become stronger and more intense, and this is from one of the research stars over in M-cubed. So that's some of the motivation, and people have probably seen this plot from many years ago of the diurnal cycle of deep convection and how, how in the daytime things are forming over the Rockies and over Florida, and then they propagate to the east during the night. And the research is motivated in a large part by the Pecan project. People probably, it's happened a few years ago, so maybe some people have forgotten, but the Pecan, there's the lead, Tammy Weckworth was involved. It was a very large project, and different people have different personalities. Some people, they do a project, they work a few years, they jump to the next project, next field campaign. And then there's other people that, you just sort of go deeper into the works to look at what's happening. And that's kind of what I'm doing here. It's research that's been kind of motivated by Pecan from what we did, but instead I'm going to be looking at these different questions. Are our nocturnal extremes increasing? And that's kind of a decadal type question all the way down to what were some of the new results on mesoscale dynamics. So those are the questions that were up there, and we'll go through them kind of one by one. So our nocturnal extreme rainfall is increasing over the central eastern US. One of the great things about being a faculty member, this is Jason Chiappa, actually when he was in high school science fair, he loves to communicate science. This is the results that I'll show are submitted by, based on a paper that he led, that several of us were involved with, and was just recently submitted to Geophysical Research Letters. And the methods, it's kind of long. One thing, we were using the stage 4 precipitation derived from radar and rain gauge, and it's about a 20-year, a little over a 20-year data set. And one of the things about having a radar rain gauge combined is when you see what these extremes look like, if you just have a sparse or a regularly shaped radar network, you're going to miss out some of the extremes. So that's the upside of it. And a downside is that with radar data, you often have errors. So the systematic errors were there, and they were removed by hand because Jason is somebody that really is very careful. But then he developed an algorithm that removed these. And sometimes this was like a point, high reflectivity and things around it, or a ground clutter that would pop up and go away, but then rain gauges nearby didn't have that. And so the upside is, it's high resolution, and when you remove the errors, high quality. The downside is it's only 20 years, and we'll touch more on that later. And for this talk, and for the GRL paper, we are focusing on mesoscale convection, and so we remove tropical, extratropical cyclones, long stratiform rainfall events with cyclones on the jet stream, local storms. And what we did was we looked at the 12-hour accumulated rainfall when it exceeded the 10-year recurrence interval at one or more grid points. And then we summed up the previous 12 hours to look at how things were progressing. And then we're looking for any points that exceeded the threshold within a radius of 250 kilometers, time frame of 12 events. And then we defined mesoscale convective systems using the Feng et al. 2016, associated precip greater than 1 millimeter per hour, and has some major axis, 200 kilometers for at least 4 hours. So kind of a long methods type statement. Again, since I'm covering a bunch of things, I'll go through a little pretty quickly, but one thing we kept track of then was the maximum exceedance above the 10-year threshold. I'll talk about the 10-year threshold in a minute. The 12-hour accumulations associated with the point of maximum exceedance, the lat lon, and the date hour of the peak rainfall. So we're looking at rainfall above a threshold, what the peak is, where it's located, when it occurred. And then just to go in here a bit, this is looking at the 10-year average recurrence interval. It's based on these studies here, the NOAA-Atlas 14 precipitation frequency gridded data. And one thing you can see if you're thinking about what's a rainfall extreme, you know, if you get the graph here, 200 millimeters, you know, if you get that, you know, 150 down here, it's something you're used to. You know, get 150 in Ohio, you know, it's quite a flood. So one thing we did was we're trying to look at extremes based on the recurrence interval and also the location. And if you live by the Gulf Coast, you know, you get some good rain. And, you know, you live in the dry part of the country, you don't. And then these are all points that exceeded the threshold. So sort of a bunch of details about how it's done, probably too quickly, but that's, you know, the map of what the June, July, August extreme events look like. And well, the question is, are extreme rainfall events increasing over the past 20 years? So this is a plot from Jason, and this is the number of filtered extreme rainfall events for each June, July, and August, 2003 up to 2022. The colors, blue represents events that it's a year that's in the low category, and then the orange is the high category, and then this is the best fit line, so they're increasing about almost 4 events per year, fairly low R squared, but we'll talk about that in a second. So there is this trend that's going on, but a lot of year-to-year variation. And so you're probably wondering, this is Jason Furtado, our stats expert on the team, and wait, are the results statistically significant? And this whole GRL project and then the thesis, which goes into some other things, actually started as a class project in Jason's class. So I think when, in Jason Furtado's class, so when the other Jason finishes up, there's going to be other papers to write based on what his thesis was going to be. Okay, enough rambling. So here, this is looking at the 3-hour running mean of June, July, August extreme rainfall events with respect to the peak correlation. And you could see, just looking at extremes, oh, you know, this is UTC, so late afternoon into the night. And then, so, you know, the extremes are, heavy rainfall tends to be with a diurnal cycle. And then this is MCSs, 10, 20 years. You can see there's a little bit of flattening. And because there's a lot here, we won't go through, you know, all of these plots too much, but this is the squared correlation coefficient. So 12 UTC, subtract 6 in there. So this essentially time period in here is the late night and into the early morning. So 6 UTC is midnight and then into the morning. So what this says is that these events, extreme rainfall, you know, it likes the solar cycle, but the changes are really happening more events at night and into the morning. So it's maybe a bit of a surprise. You're probably wondering what these events look like. And a couple things come out of this plot. One thing to me, you know, there's a lot of little speckling from short extremes, but then there's these propagating systems. And midnight to 8 a.m. is in the blue. So one thing looking at this, if you have say a climate model with 30-kilometer resolution, it's going to be good luck getting these. You can even argue if you have a 5-kilometer model, well, you're really resolving circulation 7 times that, so 30-kilometer type of model. They're going to have trouble getting that. So that's one thing that pops up. And then another is this blue is shifting eastward from where we consider the nocturnal max to be. And so it's, you know, shows a bit of a challenge in picking up these extremes in modeling. It also shows that if you have a sparse rain gauge network, good luck getting these. And then it also says that, to me anyway, this would be, some of these events would be a real challenge to get with modeling systems. And where's the trend occurring? So you can read about the stats over on the side, but this is the maximum region, and then the stippling is statistically significant. So it's kind of south of the nocturnal max and in the eastern edge of it. So it's kind of an interesting trend. It matches this to me, just eyeballing it. And then if you look at some of the flow changes, and this is using monthly averages of the European Center model, the vertically integrated water flux, you're getting what looks like an extension, westward extension of the North Atlantic subtropical high, sometimes called the Bermuda high. You're getting this moisture flowing up, and it's going right into this area where you have the rainfall extremes increasing. So, and then we looked at all these other fields too. Total column water vapor kind of matches aspects of the flow. So, all up in here, you're having more water vapor than you're used to. You're having a geopotential height tends to be higher over this, which again, maybe this is in years anomalously high versus anomalously low events. And then if you go into the flow patterns a bit more, sea level pressure doesn't show up very much, 10 meters, meridional wind doesn't show up, 850 specific humidity, you're getting this type of pattern again, 700 meridional flow, you're getting this total precip. When in rainy years, it tends to be up in this area more, the southeast is drier. So you might be looking at these and saying, oh, Bermuda high, North Atlantic high is extending eastward, but then these other years, up at 250 millibars, you do get this strong flow, almost reminiscent of more of a stationary trough or an average trough. So it seems that there's maybe not just the atmosphere getting moister and warmer, but there's tends to be shifts in extreme rainfall events in years where you have these versus years where you don't have these. There seems to be quite a difference. And you might ask, well, there's the great champion. You might ask, what about other seasons? And this is the extremes in the winter. There's a few in the southeast. Spring, it's more in the southeast again, some longer tracks, some on the Great Plains. This is the summer one we showed, and fall. It's a bit all over the place. So just answering the general question, are nocturnal extremes increasing over the central US? Yes, they're increasing over the past 2 decades, consistent with the work of Preen et al. And other studies. Statistics suggest that the increasing number of extreme events actually are occurring late in the night and into the early morning hours. And the extreme rainfall events are associated with mesoscale convective systems, but the extremes themselves are relatively small scale, which exacerbates the well-known challenge for simulating nocturnal convection in weather and climate models. And again, there's some of the references involved. And then years with more extreme events have a greater moisture flux with an extension of the subtropical high, consistent with the Zorzetto and Lee study, stronger North Atlantic subtropical high, and also the projected change with climate in the shift in the northward shift in the jet stream and the extension of the North Atlantic subtropical high. But we did see also changes in the flow pattern aloft. And to be, I think, a bit honest and cynical, we only have 20 years of data. So for example, you could make the argument, oh, we're using a high resolution, high quality radar rain gauge setup, but then, the other side of it is, well, you only have 20 years of data, so there could be other factors. Yu and Deng 2023 said an increase in springtime MCSs may be linked to increasing Pacific decadal oscillation between the 2000 and 2020. So it's maybe too short of a time to say, but it does match with perhaps what you would expect from climate change. But the the events do tend to be relatively small scale, and so far the models have been having trouble getting that. And so, connected with this, do poor forecasts of nocturnal MCSs impact large-scale circulation and forecast skill in global models? So, oh no, it's not just mesoscale, but you're worrying about convection, but what's their impact on the larger scale? And there's a picture of Sue Gray that I was mentioning before cares about really interaction of convection with a global scale. So interaction between Rossby wave packets and organized convection in the mid-latitudes can result in large-scale errors in global forecast models and even cause medium-range forecast failures called busts. And there's some of the citations that are associated with that. And how these things work, this is maybe not a good talk for EOL, even though I'm here for EOL, but a key potential vorticity structure with MCSs that impacts the Rossby wave dynamics is the shallow lens of negative PV, so that anticyclonic outflow that you get on the top of MCSs, that tends to be the thing that punches the jet stream and can cause the waves on the jet stream that move downstream. And from, again, work by Sue Gray and her colleagues, graduate students, the negative PV lens has the largest impact on Rossby wave dynamics, although these vertical columns of positive and negative PV associated with the structure of mesoscale convection can also have a secondary effect. And I'll just show a case study, and then I'll show some results from the European Center. So this is a paper, 2019. Here's 250 hectopascals, so up at the jet stream level, you have this jet in here. You have a merger with things going on up in the Arctic, and we're going to be looking at convection here. And here's the 850 flow, still that polar jet with a strong flow up into the polar regions. Not much of a jet here and something in there. And so this is kind of an ugly, squiggly diagram. So here you have the radar reflectivity, and this is every 4 hours. And then this is the southerly flow and northerly flow. So I don't know, when people took atmospheric science in undergraduate or graduate, maybe they're talking about baroclinic waves. And fortunately now, we're talking more about Rossby waves, and they're moving on the jet stream. So, and what you see with those is a southerly and a northerly. So for the people on the screen, a reflectivity here, southerly flow, northerly flow. So things start out southerly flow on the jet stream, northerly flow. So, we have a trough here, a ridge, a ridge in here. And then as this convection gets intense, the southerly winds are growing, but you start to get these short wavelength northerlies that are forming as the convection gets going. So you could see, this is really a shorter wavelength, southerly, northerly, southerly, northerly, southerly, northerly, southerly, northerly, southerly, gigantic northerlies. So you have this convection at the jet stream, you have the outflow on top that's in large-scale dynamics, a negative potential vorticity lens. This negative potential vorticity lens triggers an anticyclonic flow on the jet stream, and now you have this really strong northerly flow in a broad area of southerlies. So the wavelengths really decreased. And just to show the kind of Hofmuller diagram, here's the days, here's the latitude, so we're moving eastward. And in here, this is the zonal wind, the U wind. So every time you get an MCS near the jet stream, you're getting westerlies. So the negative PV lens hits the jet stream, you start getting an anticyclonic flow, you start getting stronger westerlies. And then this is the, kind of bizarre part. So these are the northerlies, southerlies moving along on the jet stream. Rossby wave dynamics, you can see them moving along. Mel Shapiro would be very happy. Southerly, northerlies moving here. They're propagating to the east with time. And then this period where the convection hits the jet stream, wow, you have these northerlies, southerlies that are just streaking to the east. And from this paper, now we're looking into convective parameterization, they're going around the planet in about 2.5 days. So, poof, convection, oh, the Rossby waves are moving along. Oh, we're in a regime with this merged jets, and now, the northerlies and southerlies are just flying downstream, and maybe this will help you visualize it. So, as this convection gets going, this is the meridional wind from the error 5 reanalysis. You could see very short wavelengths disturbances happen. So this is a flow regime where you're getting these strong disturbances. So it may not always be the case, but it's a really example of how, mesoscale convective systems that last for hours, what they can do to the jet stream. It's these troughs and ridges racing downstream are very different than the northerlies, southerlies, ridges and troughs. The ridges and troughs are moving downstream with time, but a new one's forming downstream, ahead of it. But here it's like, oh no, I'm just a ridge and a trough and I'm going to race downstream. And it's short wavelength. And if you look at the Rossby wave number versus the frequency per day, normally this is the kind of synoptic waves that would make synopticians happy. And then you get in these flow regimes and, the wave number around the planet is almost getting up to 15. So very short wavelength disturbances racing around the pattern. So since we have all these geniuses from EOL that work with instrumentation and measurements and know a lot more about observing the atmosphere than I'm showing in this talk, you probably wonder, a bit what this looks like. So in the beginning, you have these errors. This is an error analysis that Sam Lillo first did, but convection gets going and you have this error in the ridge. The error tends to cause Rossby waves, trough, ridge, trough, that are moving downstream. You saw that on that other picture. And then the errors, this is the plot of errors and the movement of the errors, the amplitude and movement. And then you have this big magnification over this area. So, this paper just says, oh, you have MCSs hitting the jet stream. The jet streams, Rossby waves are potential vorticity waves on the jet. And then boom, you hit it with this negative PV with the outflow. If you just have a supercell, the jet stream, get away from me, it doesn't happen. But if you have an MCS that's lasting many, many hours near the jet, it says, oh, starting to build a ridge, what are you doing there? And, these new troughs and ridges move downscale, downstream, and, it winds up, causing errors in downstream weather. This one particularly also caused a Rossby wave break into the Arctic. The errors are actually propagating into the Arctic. So that's kind of the background for this problem. So let's experiment with the world's best global model, European Center, dear friend Florence Rabier. And so what we did with Peter Bechtel, the convective parameterization, one of the world's leaders. So this is almost 2 days into the forecast. This is the error in V winds. So this is you're producing too many northerlies. This is you're producing too many southerlies. This is the old model physics that they had, 9 kilometers with the newer, which is actually the current model physics, 5 kilometers with the newer model physics, and then this is turning off the convective parameterization. So you turn off the convective parameterization, you're getting the downstream northerlies, the ridge that's, destroying Cape Cod. It's, just, you could see the error is, really, really large. So, if you're in the gray zone and we have the scalable convective parameterization and MPAS person in the audience, but it's very important to have that, so you're getting the right response. That it's not shown here, but paper that we're in revision, we're working on revisions, actually shows that if you change the resolution, you get rid of the convective parameterization, that divergence at the top of the storm changes. So remember I said you're punching it with this negative PV. Well, you turn off the convective parameterization, you might be hitting it, but you're hitting it, perhaps too high in the stratosphere, or you're not getting the jet. And there's also issues with how long things keep lasting. And then this is 5 kilometers with a newer model physics in the European Center, 5 kilometers turning it off. And this is PV. So both of them, you get ridging with the convection in both. Ridging with the convection. Oh, it's weaker, it's spreading out. Oh, it's still strong. Here's the ridge you can see. And then no convective parameterization. You wind up having this, really, really over formation of the ridge. So, you're putting too much of an anticyclone on there. The jet stream says, oh, I can make Rossby waves. And the Rossby waves are made and they're starting to race downstream. But, you turn off the convective parameterization in the gray zone, then, your Rossby waves are not right. Your Rossby waves are too strong. It's a tricky thing. So let's just maybe jump a little bit into this a bit, that the interaction between Rossby wave packets and organized convection can result in large downstream forecast errors with rapidly moving short waves. This kind of confirms the work of Professor Sue Gray out at University of Reading. Going back to some work by Joe Trivia, errors in climate models were found to be associated with rapidly moving Rossby waves generated by diabatic heating. This was in the days after when AAP was around. It's after that, but the Thorpex was going on, and there was CGD and M-Cubed were collaborating, and Joe looked into this and said, oh, diabatic heating can generate rapid Rossby waves due to convection. And interestingly, it's George Bryan. It's been known for quite a while, and there's a lot of other studies since then that have done more refined look. But turning off convective parameterization in the upper end of the gray zone, and maybe that's even throughout the whole gray zone, 1 to 5 kilometers, can result in more intense and elevated divergence at cloud top. And the differences in cloud top due to grid spacing has been long known going back. So if you have a regional model, run things at 3 kilometers, it's kind of fine. You have a global model, 3 kilometers, you may be changing that divergence up at the top, and you could be, if it's near the jet stream and long-lived, you could generate some pretty big errors. So, I did say that these were too many slides. So this was a period with a merged jet, and the convection caused errors on the jet stream. Some leaked into the Arctic, some moved across Europe and resulted in a forecast bust. I'm not showing that here. So, you're talking about regimes where there's likely to be forecast failures. And Chris Rattray, it's a modern world where we work on. So a master's student can be using AI and say, I might look into a private sector job. 4 days later, he's hired at high pay back in his home country of Canada. Oh, that was a nice job, but not so good. I'm going to go spend a month at my parents' small cabin in the Canadian Rockies and come down and look for another job. And within a week after that started, I think I had 3 phone interviews and a Zoom call to look into Chris. So Chris jumped to another thing. So we're still kind of looking at a replacement for Chris to finish this work. But Chris was looking at the European Center interim reanalysis. He was looking at the forecast bust, Mark Rodwell's criteria for forecast bust, forecast failure in medium range. And he trained it on 1,200 busts, poor forecast, twice as many non-busts, and then tested it on 57 dates. Looked at a whole bunch of fields and found the UV and geopotential height at these fields were really important. And if anybody knows about AI out in the audience, you probably know more than I do, but this was the architecture that Chris used. And then he was also using heat maps for the convolution neural network to say, why did you make this decision, bust or no bust? And so these heat maps looked at different levels, and very often the levels where it found things were important were again up near the jet stream where you would kind of expect it. So this is 300 hectopascals. Ignore the wind barbs, they mean something else in this. But here's the geopotential height, so it's getting this split flow, getting this merge flow right seems to be important factors. And prediction accuracy, Chris did a lot of tests, but around almost 90% of the time you could identify a bust. And we're redoing these calculations with the error 5 using the best and the worst. So Chris started on this, and first he showed me a Bitcoin prediction and said, oh, here's the Bitcoin, it's moving along. The Bitcoin price did this. I just shut my computer, it's no good. And then he said the next morning I opened it up and this is what the Bitcoin did. It laid right on the line. So he said, so I got into AI and I think I'm going to be able to use it on the European Center forecast. And so for a long time we were using this on our own computers rather than at OU. Chris wanted to start a company and sell it. Maybe that would have been a better idea, but it turns out that we're redoing it with error 5, the newer reanalysis, and the best and worst. And Chris was rapidly employed in the AI world and quite happy back in Canada. So anyway, it's interesting because it does well on predicting 5-6 days ahead. Is there going to be a forecast failure or a good forecast? Many days ahead, and it tells you what character of the flow helped with these decisions. All right, so MCSs can impact Rossby waves. I'm so sorry, I'm giving this talk to EOL and it's all about Rossby waves and climate. Oh, it's terrible. Now you can see why they chased me out of here to go to Oklahoma. But we know MCSs can impact the Rossby waves, but the Rossby waves impact the nocturnal environment. This is going to be very short, just a few slides. It's a paper that we're going to be submitting soon. Alan Shapiro, the dynamicist equation man, is over here. And we looked at an analytical model looking at the timing and strength of ascent, subsidence, nocturnal low-level jets. And what he essentially did, he had people look at Rossby waves and its upper-level dynamics, ridges and troughs moving downstream on the jet stream. And Alan said, well, why don't we put in a diurnally varying boundary layer and see what happens? What's the Rossby waves going to do to ascent? How's that ascent going to change the low-level jet? How is it going to ascend, change it to, help the low-level jet, help to ascend? What's it going to do to Rossby wave structure? And because it's Alan and his analytical studies, the flow is actually neutrally stratified. There's no horizontal temperature contrast. So we're just looking at Rossby waves move. And Alan is including me as a co-author because we talked a lot about this. And the math is just, so the paper's on my computer and I'll read it while I'm out here. But, essentially the idea is you're looking at Rossby waves and putting a lower boundary in and a diurnally varying lower boundary. Let's see what happens. So this is Rossby waves at 2,000 kilometers. The yellow lines are sunset, sunrise, black lines are sunset. And this is the U wind and the V wind, northerlies, southerlies, Rossby waves, north and south, and the ascent. And you can expect ascent with a Rossby wave moving along. But it turns out the ascent tends to be low level and last into the night. So this says, these large scale waves, when you have a lower boundary, you can actually wind up getting changes in the jet. You can get changes, which you would expect, southerly, northerlies moving by, but you actually get ascent during the night. So this is 2,000, and there's happy Alan, happy with his analytical results. And this is with 6,000. So again, 6,000 kilometer long Rossby wave. Here's the U, and you do get this change in U that's a bit surprising. And then you also, black line, you're getting changes in ascent, ascent that also varies as this moves by, so, ascent into the night. So it turns out, the proud large-scale dynamicists and the Rossby waves, and Sir Brian Hoskins, who's, somebody I know, almost consider each other friends, but let's make it more complicated. Let's put a diurnal boundary layer in, and look at what you get. You get ascent at night. You change the low-level jet. So Tammy's been sitting there saying, Dave, anything closely related to pecan? And so I guess I have a little bit of time, so I'll talk about a little bit of the mesoscale dynamics. And people know, Kevin Haji went off to University of Washington, got hired by Amazon. It's the new world we live in. And he was looking at these density currents, and density currents going into a stable environment can trigger bores that move out ahead. The bores are a lot of lifting, and they have structure from a single bore to undular bores to solitons that are increasing with time. So I won't talk about this, and part of bores, it's in the literature. And this is a picture. It's hard to see. This is Sushi Zhang. This is what happens when you have grad students, right? They get their doctorate, or you have to take them out to a nice dinner. And this is my wife, Joyce. And here's Kevin Haji, 2 other students. And it's kind of surprising, but bores can occur in stable layers aloft. And this is out of a paper, Zhang et al., 2019. This is a horrible plot. The potential temperature, and this is ascent and descent. It's kind of hard to see, but you wind up triggering a gravity wave, a density current, that moves out. And then you get this ascent that moves out ahead of it. So you get this ascent in the mid-levels. This is kind of a simple environment. Amanda Chastain's here, and she looked at a convective system in an environment that was evolving with time and space. And it's still trying to understand that paper, but I'm starting to cite it more because, it's actually it's linked to something, some Chinese results that we're working on. Just shows you how complicated it is. So anyway, you're getting this ascent in the mid-levels, and the reviewers of the paper said to Sushi, well, put in some orography and a neutral boundary layer and an inversion aloft, and you could see this ascent moving out ahead and away. So you can get, with neutral boundary layers and ping from a mountain or a ping from convection, you can get these bores that are moving out through the mid-levels. So this is, it tells you how terrible nocturnal convection is. If we think of convection putting out a gust front, and sometimes nighttime convection's working that way, but other times it's triggering bores. From Amanda's work, they vary in space and time, the boundary layer, the environment's changing, and then you can have these gravity waves generated by convection, but then you can have what looks like just a bore, an upward ascent moving away. So it's another thing that's coming out of this is there's work more to try to get the climatology of bores over at different locations. This is another work by Sushi Zhang, GRL 2022. It was a multi-year investigation looking at bores over the southern North China Plain, 2015, 2019. The structure really depended on location. Undular bores were near the coast, non-undular to the west. Bores were most likely to be active June and July when convection was there. The bore frequency is lower than over the southern Great Plains, but it's super sensitive to synoptic regimes. 80% of them were occurring in 4 to 5 day periods. So, and this is a non-hydrostatic phenomena. Even in a 3-kilometer model, you're going to have trouble getting the bores right. Some people push towards a kilometer or less. So, just certain times you're getting these kind of lifting events, and they're just in certain periods, and they had shorter duration than the southern Great Plains. The southern Great Plains, the bores tend to move strongest to the south, and they're kind of an arc, sometimes moving to the southwest. Over China, they were moving in all different ways. North of the Mayu front, they're heading to the south. south of the Mayu front, they're heading to the north. So again, mesoscale dynamics are, really a complicated, complicated subject. And the Mayu front is very different than the nighttime convection over the Great Plains with our low-level jet. So just maybe a couple slides more on mesoscale to keep Tammy happy. We're looking at Mateus Gomes from Brazil, his CM1 idealized simulations. It's looking at how conditions vary in a non-uniform environment. You have a high soil moisture and vegetation to the east, dry conditions to the west like we do on the sloping Great Plains. But with CM1, we're just using a flat slope, and turns out this kind of a thing, you get a dry line. You get a convergence of the heating, so you get a dry line type structure during the day, but then at night it goes into a internal gravity wave mode where you're getting ascent. This is pretty similar to the analytical study by Allen, but this is a CM1 study, so it's suggesting that you go from a dry line to mesoscale ascent like a gravity wave. So convection moving from the west with the plains, it's moving to the east, it's going to die out. This dry stuff, how's it going? The mountains really got me going. And then it gets near the moist air, and it's like, there's ascent here. This helps me along, keeps the things going. And then it keeps it going, and then it gets into the higher moisture, and it keeps, nocturnal convection can keep going. In a sense, you might be able to trigger convection with this ascent. And then there's a lot of work that dynamicists do, and they're looking at the low-level jet, and they say, turbulence turns off, and you go through the Blackadar oscillation, and the Holton mechanism helps with the slope. But it turns out conditions can be highly nonlinear on the slope, and things are advecting. So the geostrophic wind is really varying like mad on parts of the slope at night. So if you're just using the Blackadar mechanism to predict the low-level winds, the VG's changing during the night, and that really does make a difference. Then another thing from Chris Rattray's thesis, again, Chris got hired in the AI world and left us. So this committee said, there's at least 3 papers in this thesis. So, but anyway, long-wave radiation matters for the nocturnal low-level jet. If you have moist air, you're not cooling the surface. You're keeping the surface warm. You're bringing in a strong jet. You're bringing in more warm air and moisture. You're not getting much of an inversion. You get a lot of mixing. So the radiation budget does tend to matter. So the rambling ideas, nocturnal extreme rainfall events seem to be increasing over the central and eastern U.S. It seems to be associated with the change in the North Atlantic subtropical high, associated also with the movement of the jet stream to the north. But there could be other things going on since we only looked at 20 years. The MCSs do impact the large-scale circulation and forecast skill in global models. If you're at the higher end of the gray zone, you better have a convective parameterization because you wind up getting the Rossby wave too strong, a big ridge, northerlies coming down, going over Rhode Island to Long Island and all of that. So, getting this nocturnal convection just right really seems to matter. And it's, as Chris's work shows, it also depends a lot on regime. Rossby waves do impact the nocturnal environment, at least in an idealized sense. It changes the ascent, changes the low-level jet, and there is a little bit of new results on mesoscale dynamics, and then just putting something up at the end. It seems like extreme rainfall events are more likely in our warming climate, but getting these convective events just right and getting their impacts on the global circulation is still a major problem. So thank you, and sorry I was jumping all over the place. So different people have different personalities. There's the observationalists. They do a field project. They work on it 3 or 4 years on to the next one. And, my mind works so slow. It's like, oh, I'm still working on things that Pecan made me think about. So thank you all very much.
Oh, well, thank you, Dave. Your animated seminar got us all excited about Rossby waves. We have plenty of time for questions. John?
So, hey, Dave, nice talk. So it's been 7 years now since Pecan. What's the current thinking as to why this nocturnal convection takes place? And do you know more now? What's forcing it, or what makes it happen?
The trigger of nocturnal storms, there's still a lot of work to be done. We have the storms moving west to east. The fact you have a low-level jet and you're not enough radiation, you're not cooling the surface, so it's almost like having a happy daytime boundary layer, just a little more stable. But there's still this CI, convective initiation, that happens during the night. And there's still, some debate as to why this is going on. Dylan Reef has published some papers suggesting that there's an internal gravity wave response. So I think that enough of it's mesoscale. If you have a really good nocturnal boundary layer and you're getting the surface right, you're getting the advection right, you should be able to do better with it. The European Center improving their convective parameterization. They're getting the systems lasting later into the night, but there still seems to be a problem in global models with, getting this nocturnal convective initiation, getting the, for a parameterized model, you can almost say forget about it. You're maybe thinking of an outflow, but you're also getting bores, you're getting, gravity waves from or bores in the mid levels. It's a real mess to try to parameterize this, all these variations, dynamics that happen at night. So maybe I think the hope is to move to high resolution global models, and I know that that's happening a little bit in this country, and the European Center, I think, is pushing the digital twin that's going to be at 1 kilometer. So,
is this a phenomena that's just particular to the high plains, the central plains of the United States, or are there other geographical locations around the world that see similar phenomena?
Yeah, so some of the work on getting things right, there's the over South America, you have this nocturnal convective max that's still a challenge. Over parts of China, over India, it's still, nocturnal convection, I think Peter Bechtel would argue, is, it's a problem at all the land locations where this is happening. And it's easier if you think you're heating the boundary layer, heating the surface, capes going up, convective inhibition's going down, but then you get this weird dynamics at night. You've got to maybe get the Rossby waves right, getting the surface radiation right, turbulence right. It's not just an outflow, and sometimes the outflows dominate, sometimes the outflows cause bores. The paper, I didn't show any of this at Dylan Reef's paper out of his dissertation I'm a co-author on, and it also looks at the difference in bore movement and bore ascent, how it varies along the leading edge. So it's kind of a complicated mess, and hopefully high resolution models with good physics will do better. It's not a great answer, sorry.
That was a good question, though. That was a good question, John. Thanks. I'm going to switch to online. We have a couple of questions online. We have one question from James Pinto who says, very interesting talk, 2-part questions. Number 1, were busts predicted by AI related to short-term prediction errors in the evolution of MCSs? And number 2, did you find a relationship between the bust predictions and the EC ensemble spread?
So that's a great question, James. There's other work related to Sam Lillo's dissertation that suggests maybe the busts are rooted in convection that starts over over North America, but actually the big issue with the bust is actually the error growth over the North Atlantic. And this seems to be getting Rossby wave breaking right. So we went into this thinking it was all convection over North America, and that helps sometimes with the initial error, but it's really that, the North Atlantic jet comes into Europe and conditions are different, and, the Rossby wave is moving along, and then the Rossby wave breaks. And getting that Rossby wave break seems to be a big part of it. So it's not just the MCSs, it's just the large scale flow. And the relationship to bus prediction and ensemble spread, that's something we haven't looked into. We'd like to, but downloading the 51 members for 20 years is, I think, would fill up Cheyenne a bit. So we haven't done that, and that's a good question. And what we're actually doing, though, is looking at the best versus worst forecast. No, we should be looking at the ensemble spread, but we don't have the computer capacity, so we start with the deterministic.
Right. Thank you for that question. Do we have a question from the audience? So I will turn to the virtual screen. We have a question from Jürgen Jensen, who says, "Hi, Dave, interesting talk. The impact of MCCs on the jet stream must depend on the altitude where most of the convective air ends up, the negative PV lens. The convective parameterization has to get that level right, but how good are the convective parameterizations, in particular for MCSs?"
So, Jan, that's a great question. I wish you were here, or I was in Australia, not giving a talk, but just sitting down and chatting. So the convective parameterization does better than turning off the convective parameterization at 5, probably 3 kilometers. So it helps, but it doesn't, I think it probably doesn't help as much as a high resolution model that's doing that. So, and that's, I think, one reason I'm going to talk to some of the scholarly folks in M-cubed, I think, to do this with MPass at different resolutions, turning on and off the convective parameterization. So I can just say from this one regime, the convective parameterization helps, but doesn't quite get it right. And improving the convective parameterization, which is hard at night with all this other stuff going on, or going to high resolution is probably the best thing.
Okay. Thank you for that question. Do we have any questions in the audience? We have a question from the audience.
Oh no, this one scares me.
So going back to Pecan, was there anything learned from Pecan in terms of what additional observations might improve the ability to forecast these nocturnal systems?
So I think there's work being done by others on that question right now. Risto Chapilski, who's not here today, but will be back tomorrow from his travel, has worked on that. And I think doing the soundings, observing the lower part of the troposphere helps. And I think Tammy probably has a better answer to that than I do. But I think the soundings, getting the lower troposphere right really helps. But, on the other hand, I think, getting the variations in the stability, variations in the jet, sometimes that jet instability is really pretty narrow. So I think it's helped saying that, well, mesoscale observations, not just the surface, but the lower troposphere would help. But Risto's work was suggesting it was complex, sometimes the winds, sometimes the stability, et cetera. Tammy, you want to add anything to that?
And we have a question online from Ian Cornejo, who says, is there evidence of advancements to the NexRad network increased number of rain gauges, allowing for better captures of EREs, possibly accounting for some of the increased climatological frequency?
Yeah, that's a really good question, and that's something that is, I think, worrisome because maybe it's not maybe the extremes aren't increasing, but other observations suggest it's so. What we really saw was that the number of garbage in the extreme rainfall, and sometimes you could tell it's just spots around a radar or a mountain that always stays. So I think with the removing the artifacts became easier with time, and hopefully I think it allowed the better capture of the EREs, but hopefully it didn't impact the climatological foundation. But that's a good question. It's something we worried about a lot, and it's one reason Jason went through by hand, looking at not just the stage 4 products, but actually looking at the radar plots for each of those cases, and then building an algorithm to get that. So I think it's the advancements to how the radar data is possible, the number of rain gauges has helped, and hopefully it doesn't account for the increase in the number of extremes. But it did seem to help with decreasing the number removed. And I think the GRL letters, the supplement, shows what some of the garbagey ones look like. But it's a good question, and it's something we worried about a lot.
Well, with no further questions, I'd like to thank Dr. David Parsons for coming to EOL and to give a seminar. For those of you who are interested in his research or who are curious about his stint as a United Nations diplomat, Dave will be at EOL this week. It is spring break at OU, so let us thank our speaker one final time.
And thank you all again. It's good to see some of your faces, and thanks. So.